So this semester, Roy is going to graduate. So I'm going to organizing a GSS and looking for speaker and monitoring tools. So if you have any suggestions, please let me know. And also, if you have any good topics that you want to talk about, please let me know. So today I'm going to talk about connection between fluid and reflective Brownian motion. So which I will usually abbreviate as RDF. So let me give you not a motivation, but the reason why I'm going to start this studying this problem. So actually it comes from an oral exam. There's an ugly question. I will write it down here. It's really the boring part, but hopefully you'll get better. So we have a stochastic process, xt. And it's given by this way. Mu t plus, let's say, bt, and b is a Brownian motion, standard Brownian motion. And then plus two process, lt0 and minus lt1. Where the LTs, they satisfy these properties. So each of the L's, they are increasing. And they keep X within the range of 0 and 1. For all the time. Because Brownian motion can go really wide, right? It can be as large as you want. And there's a J, mu t there. So mu t plus bt is not within the range of 0 and 1. But after we add and subtract these two processes, it's within the range of 0 and 1. And also, is the minimal. Minimal in the sense that because it's increasing, right? So you can think of it as the total variation of the is the minimal processes that 1 and 2 holds. 1 and 2. Oh, by the way. And starts at 0. So I see many confusing places, and that's why I want to miss. I'm not too stupid because I don't even understand it the first time I look at it.
So what's the problem?
Sorry, what is mu? Mu is a constant. Okay. So the problem x is something like this, and then L is some real function that satisfies these properties, and then the question is, what's the distribution of xt? Something like that. It's a stochastic process, so and x takes value between 0 and 1. So you must have a distribution, right? Basically a measure of 0 and 1. So it's asking what is that. Okay, so the thing is that I don't even understand the question. What is LK dot? Right? And if I tell you something else, then you recognize it immediately. Okay. Alternative way. Or say the question.
I can barely see. piece of chalk. We can.
This is probably.
Okay.
Okay, the alternative way of saying the question is that the number xt is away from 0 and 1. It behaves like a drifted Brownian motion. Something like this. Okay. And whenever it hits 0 and 1, it got reflected immediately, intuitively speaking. So basically, x is a Brownian motion. With drift mu and is restricted in the unit inflow.
Do you want to add in your list of assumptions that LT0 only increases when xt is at 0? Or is it you're saying this follows?
It's the minimal such process. So it's the minimality that guarantees the probability. So you see our professor is giving me a hard time by trying to describe the problem, but he tries to do it in a confusing way. So, yes.
So does the direction of the drift flip on each reflection? Or is it constant in one direction?
So, yeah, so the picture is something like this. So let's say you are drifting up. And whenever it hits boundary 1, it got reflected, but still the train is going up. So you have a positive drift, it's more likely that you will stay close to 1 instead of close to 0. Yes. Okay. So that's the first problem that motivates me to study reflected Brownian motion. I find the description in this way is really confusing because of this L is given in such a way. So I'm saying that that's actually not the way to study Brownian motion, reflected Brownian motion. And we look at a better way to do that, which is the queuing. A better way to look at a better way of defining reflected Brownian motion, and it shows that why people outside of probability should study something like this. Okay. So, well, forget about all this crap, and you can see that there's a single queue or a single storage facility. A single queue. And here's the assumption they make. It has infinite capacity. Meaning that the goods in the storage room or in the queue can build up larger as one. There's not a quota. There's not a limit on the storage. Okay. And the second thing is that the inflow and the outflow are very different. So the inflow, what's the inflow? Inflow is described by a sequence, which inflow is given by A, I guess is arrival. And outflow is also a sequence, which is given by R, I guess is release by N. And the assumption is that these two sequences are independent, and also the sequence themselves are RID. And you assume that they have finite cycle moment, so you can talk about its variance and also its mean. Its expectation and its variance. So, okay, so stuff comes in and out. And what you're interested in is that how many stuffs is in this queue at time n.
So there is a clock, ticking clock, and at every moment you have an inflow and outflow, and then you update your image at the storage. Okay.
Yes, exactly. And the clock here is this group. Yes.
So do we know anything about the distribution of AM? These
Here,
are just any
like, you assume that it's ID, and yes, if you want, you can say it has a PDF. Here is an F PDF. Here is PDF G.
Okay,
It does
can
not
you-
really matter because we will later take into the limit.
I'm confused. AN, this is A at the time N, not the nth, the time of the nth entry.
Sorry,
The
this
arrivals at
is-
time intervals.
so
Oh.
So we have time intervals, and AN is how many arrivals we have in
At time interval, time N.
yeah, how many stuff like let's say apples, we should say. The AN apples arrive at
Time N.
and
But
yeah,
the amount of stuff is continuous?
Hmm?
Is the amount of stuff continuous?
that depends on this. You can think of it as continuous until the water.
Okay, but
Apple
the
you
time
get
is discrete.
yeah times this.
And what if Rn is more than, like, what if Rn is more than, I don't know,
Whatever in
N?
the storage, right?
Yeah.
Yeah, so that's the part. That's the reflected part. That's a good question.
Oh, okay.
Yes. So we are interested in whatever materials or whatever stuff in the storage at time n at the step n. So let's say it's Wn. Okay, so W is 0. Let's assume that it's 0. It doesn't matter. It's just an initial condition. Okay. So at time n. Okay, that's whatever I have at time n minus 1. And then AN arrives. That's what I have right now, right? And then there will be an outflow demand of Rn. And if the sum of Wn minus 1 and An is greater than Rn, then just subtract it. That's perfectly fine, right? If I don't have enough stuff to fulfill this demand, this release, fulfill this outflow, then I just drain whatever in my storage, right? And that becomes 0. Right? And the rest, the difference between Rn and the sum of Wn minus 1 and An, I cannot fulfill them. So that's the part, that's the answer to the question the same answer. Well, if this guy is less than that, well, you do just do nothing. Just give whatever that you have in the storage. And take the positive part. Okay. So, this inductive formula governs the dynamics of the stuff in the storage room, in the queue. And let's say you are interested in the long-term behavior of Wn of the sequence. Interested in this long-term behavior? Right. So the inductive description is not really friendly because you have to do it from time 0, right? But you will not care about whatever happened initially, you are happy about its long run. So probably a good idea is to take it, bring it to a continuous time case, right? continuous approximation to use continuous version to approximate this discrete problem. So the idea. Use continuous version to approximate the discrete harmonics. So now, if you think about this, I should write it as WN minus 1 plus UN. And UN is defined to be the difference of AN and I. And then if I drop the plus sign, then what would the process look like? So if I have a new process, x0 is 0. And xn is xn minus 1 plus un, but without the truncation, without the positive truncation. And this guy, xn, the sequence is a random walk. Because ANs and RNs, they are IIDs. So this sequence is a random walk. And we know that random walk its limiting case is Brownian motion. And here, Wn is almost a random walk, but it's restricted to the half space. It's truncated at 0. Right. So we should expect, reasonably, we should expect that we should expect that Wn, well, let's leave it. I have a quotation here because it's not exactly this one. Approximates Brownian motion restricted on the half space. That's what we should expect. And now I'm going to give a quick proof why this is the case. Well, it's not a rigorous proof, but it demonstrates the idea. So here, the random walk approximates Brownian motion is done via this way. Is you consider the sequence, but here this is a continuous time process. You scale it properly, so you scale it by the square root of the index. And then here, you take the integer part of the time. So you accelerate the random walk, and then you scale it by its value, by its standard deviation. The sigma is the square root of the variance. So it's the variance of UN. Okay. And now this guy, the rescaled version of the random walk, its limit will be a Brownian motion. That's already well known. So for Wn we do the same scaling. Oh, by the way, here it goes to Brownian motion. Actually, with a drift if the expectation of UN is not 0. So here, let me make life easier. Assuming that goes to Brownian motion, assuming that the expectation of AN is the same as the expectation of RN. So the arrival is the same as the release on average. So you somehow expect that, like in the long run, right? If you don't truncate it, whatever left in your storage room should be 0, right? And that's reasonable, don't you? So if you assume that, there will be a long motion. If you don't assume that, then you will have a drift. Now do the same scaling for W. The same scale, and I want to show that this guy, the rescale version of Wn, it has a limit. So what I'm going to do is that I want to rewrite Wn in a closed form. So here's the integration. What's the closed form of it? Let's say here is the trajectory of x. That's what x behaves as n increases. Right? Now I want Wn to be strictly positive, right? But I want to keep this behavior. So basically, when x increases, I want W to increase, right? When x decreases, I somehow want W to decrease, right? And by the same amount. So here I have some negative part. So what should I do? How about I lift the whole path up a little bit, so that the lowest point is positive, right? So I don't have another color on that, right? Yes. So how about I lift the whole path up? So this is my new 0 level, right? This one. But originally here I'm positive, so I don't have to shift my ground levels down, right? So in this part, I'm perfect. Okay, this part I have to lift my ground levels down a little bit, right? So at this time, my 0 is right here. And then as x decreases, furthermore, I lift the path up a little bit. Basically, I shift my zeros to here. Now that my 0 is here, and x increases, right? So it's strictly positive with respect to this new zeros, right? New ground levels. So I'm fine. So I just keep it as it is. So
Why do you have to make everything positive?
by plus a shift, right? By plus a shift to the path.
Yes, but so after you do that to x, how is that related to
Whenever you hit a historical minimum, you update the lowest, the baseline.
Yes.
So that's how you get from x to n to wn.
Okay.
Yeah, I will write it down for you. So So that's the idea. And as Ron mentioned, the idea is that whenever x hits a historical minimum, I just plus the negative part of this thing, shift it up. So here's what I'm going to do is there's the negative part of x plus the original trajectory of xn. So this part, this running maximum or running minimum, corresponds to the shifting of the baseline, shifting of ground zero in this picture. So I'm claiming that the claim is that this thing xn plus the running maximum of the negative part is the same as wn. And the quick proof is by induction. x0 equals to -0. That's fine. That's by our definition. And then Wn, our definition is this one. Wn transform is un, and then take the positive part. And the inductive hypothesis gives me the Wn-1 is Sn-1 plus the running maximum of the negative part of x. So here, xn minus 1 plus un will be my xn according to the definition up there. It's a random walk. Right? And here, the truncation is effectively the maximum of 0 and the sum. Right? So I can take out the xn and then plus the maximum of 0 minus xn and whatever the running maximum, the previous historical maximum. Minus yes. I just pull the xn outside of the maximization. And here, by the definition, I prove what I claim. So this formula is true. The sum of the running maximum of the negative part and x itself is wn. Okay, so now I'm taking wn to the limit, right, after scale. But I know that this one, its limit is a Brownian motion. This one, okay, there's a function applying to that, but this function is nice enough. It's continuous. It respects the limiting processes. So I can also put the limit sign in. So the conclusion is that if I scale wn, its limit will be the limit of xn, plus its running maximum of the negative part. show that the limit exists. And it's related to a Brownian motion in such a way. And you should expect that, actually you don't need to expect that. You know exactly that this thing behaves like ET whenever the running maximum is not hit. So whenever you stay away from the zero. So whenever your increases, in this part, the limit just behaves like a Brownian motion. The reflection is done when it hits when it surpasses the historical. Any questions? So this one. To address our original question, what's the long-term behavior of WN? Let's say if I want to study let's say 2016. I want to study its distribution. I want to find its PDF or PML. So what I can do is that I consider this guy. And this one is approximately it's not approximately this one, but it's exactly the same as this one, and I can approximate this one. Hopefully, like 2016 is large enough. So let's give a name here. CT. Because like this one is Gaussian, this one is just a running maximum. And actually, its distribution can be computed. So I have an understanding of the distribution of W10. That kind of uses the idea how we can approximate the discrete case using the continuous case.
This is an unclear question, but something bothers me about this when there's drift, because I feel like there's something else has to be done, because if there was downward drift in this thing, this process, we would be stuck near zero.
Yes.
But if you reflect a downward drifted Brownian motion, you go to infinity.
Nope.
Because
okay, so here the reflect have to be careful about. We are not taking that I have a trajectory like this. I'm not reflecting it. That's not the thing we are doing.
okay.
Here is more like lifting. We are lifting it to zero, but no more.
Okay.
Because when people usually think about reflective Brownian motion, they think about they think about taking absolute value, right?
Yeah.
They think this one is the reflective Brownian motion. Okay, that's correct when you don't have a drift. That's a reflective Brownian motion. But whenever you have a drift and you take the absolute value, it no longer is a reflective Brownian motion, because when it hits zero and it tries to go down, I'm making it going up. That's it. So this one is not what we want. But if you use the formula, you're adding the Brownian maximum of the negative part, which corresponds to the idea of lifting, then it will behave as you expected. So it will start at 0.
Yeah, okay.
So this is just a big example. And now I want to generalize a little bit. So one direction of generalization is that I now have a lower bound, right? So I want to add upper bound. So upper bound, let's say 8. Okay. So you can still write down the discrete time dynamics really easy just by having a minimum, right? Truncate it from the top at A. Okay, and using, well, not exactly the same argument, but you should kind of hope that this guy scale copy, it should have a limit. And this limit will behave as expected, which is restricted between 0 and A, but behaves like a Brownian motion in the interior. And when it hits the barrier, it's like, when it hits the barrier, it instantly goes down. But if you have a drip, it will preserve the drip and stick to the boundary, which is originally the question I got on one of the previous orders. And you see that how they describe it in a really observed way. And actually, if you want to write down the L's explicitly, it's really observed. And actually, there's some formula before 2016, but a nice formula was published in 2016. So 2006, not 16. 2006. So actually, it's a paper by Schiff and some others. So it says that if I have a function xt, let's say it's continuous. Okay, and I want to restrict it between 0 and A, and in such a way, which is in the interior, it behaves just like X. But when it hits the boundary, it got reflected. So ZT is such a process. And how do I get ZT from XT? So the paper says that it's something like this. Let me see if I can try to write it down. So the supremo of 0S, and then here is XS minus A. Then we have an infimum. U runs from S and T, X U. And then almost the same thing, but with a positive sign out there. function, or you want a process z that behaves like x between 0 and a, excluding the boundary, but you want the process restricted between 0 and a. So, and as you can see, that it's really ugly in this sense. But if you do it in the discrete case, this is maximum, minimum, and you can prove it by reduction. Really easy. Using that formula, that definition. Okay, so that's one direction of generalization, which is ugly, but it has its applications. And by the way, this correction term that makes x stays within the range 0 and a is called a Skorohod map. And in this case, you have two boundaries. So this bunch of jump is called double Skorohod map. And this guy, the running maximum of the negative part, this guy is called the Skorohod map. So, in general, let's say you have a process, xt, and it takes value in the Euclidean space. And if you want to restrict it to omega, and such that zt behaves like xt in the interior, so got reflected at the boundary of omega, you would lie a function. So the crash term. So this yt is called the Skorohod map. Of course, it depends on the domain, but not on the function. Well, depends on the function, but the Skorohod map is whatever x opposite of y. That's the Skorohod map. And which is the approach to define Brownian motion, starting with define a reflected Brownian motion starting with a Brownian motion. But as you can see, this one is really ugly and it's really hard. But if you consider the discrete time is the approximation, then it's easier to understand. And the existence of Skorohod map is, as you can see, is not easy. It's really abstract. But it exists actually. So that's why you have the original ugly definition of it.
So omega is a compact subset or what? What is omega?
Omega?
Yeah, can it be?
It need not be compact. Actually, the half space is easier, right? Or quadrant.
Oh yeah, you're right.
Is it necessarily an intersection of half spaces?
No.
Okay, so you can have like a sphere or something.
Sphere.
Okay.
But I don't know what's it for sphere. But talking to your question, half space is usually a case because people study reflected Brownian motion. The motivation is to actually approximate the Q, the behavior of the Q, right? So actually here comes the funny part, the higher dimension. Q is a pain, R2. We consider a model of two Qs. And then we see how things becomes a little bit more interesting. So, okay, so now you have two Qs, and both of them they have infinite capacity. And as before, there's some random but independent And between these two q's, let's assume that the flow is always a constant. It's a C, and to make sure that there's nothing built up or nothing built out, let's assume the expectation of AN is equal to C, which is expectation of Rn. So you kind of expect that there's nothing accumulates or drains out. So now you want to study whatever inside the first loop, with bracket 1 and W2, and you want to study the joint distribution of this thing. And now you want to write down some difference equation, and then want to limit the limit, and see if the limit corresponds to whatever reflected Brownian motion in the first quadrant. So the first component is so this one plus AN minus and truncated 0. And this there are like, so you expect that the first component is a reflected Brownian motion. And second component, a bit more interesting. So you have this, and then the inflow looks like C, but it's not actually C. Right? Because if whatever in the first Q has some, this quantity is less than C, right? Then we take a minimum. So it's the minimum of built-in. That's the inflow.
Shouldn't it be n minus 1?
Depending how you.
But otherwise, like when we empty the first queue, we kind of want the things that we have in the first queue that we empty to go to the second queue, but the way you've written it, we've kind of already taken away those things when you compare and take the minimum.
I don't think it should matter in the scaling limit.
Yeah, in scaling rate, it does not matter at all. So that's a good thing.
Because
That's
it's
a good
dividing
thing.
by
I
a
should know
big
this.
thing, so like one step won't really make a difference.
Actually, let's do it this way. That makes sense. Okay. Minus. Okay. So this one is understood. This one is not, because changes in the first component affects the second component. Changes in second is not affected. Okay, so now in the same spirit, these are defined effectively. So we want to find a closed form formula. For the first one, we already know that, which is is equal to x1n. We should know how to define that. Plus the maximum productive power. Okay. The second one I'm not proving for you because it's tedious. It's not interesting. But it's something like this. So xn2, I think it's plus
obvious one.
of the first component.
You can think about Wn1 and Wn2 combined, and then use the previous formula, and then subtract your Wn1. Then you get your W2.
Yes. Okay. Yeah. Okay. So that's a better derivation without using induction. Yes. Just consider sum of it, which is
The sum of it
has the same
yeah.
dynamics as the
Previous.
first Q. So now we have this way. So this one corresponds to the reflection of the second component going up. So this one is that whenever the second component hits 0, it should go up. So let's say it's And now, whenever the first component hits 0, you will have a reflection in this direction, in the positive x direction. But we also have a decrease in the second coordinate because of here. Right? This, sorry. Yeah, this is the correction term when W1 hits 0. It also appears in the second component. So the reflection actually is not normal to the boundary. Which is oblate reflection. And I think it's a cute way to like come up naturally what an oblate reflection is. So that's one way to show that. Okay, so now you know the dynamics, the continuous approximation of the discrete. So the Q, whatever in the Q, it behaves like a Brownian motion inside the first motion in ATM. The funny part is that whenever the first Q is 0, the second Q, the material in the second Q actually decreases. So there's a funny thing here. And now, maybe people want to ask a question now. So, will there be a time that both of the Q's are empty? So, basically, it corresponds to the question of whether the region is hit. The region is hit eventually. So, actually, there's a very cute result here. So, it says that in R2, if I have a wedge, like this, and this angle is this, and I have some Q model whose limit is limit is some oblique refractive Brownian motion described by this, which says that the angle of the direction of reflection between the direction of reflection and the normal vector, one is theta 1, one is theta 2. And if I look at this number, the ratio of the sums of this angle over the angle of this wedge, if alpha is greater than 2, then actually their region is an observing state. Basically, it says that once you reach the region, you stop there. And if alpha is between 0 and 2, strictly between 0 and 2, then the region will be hit, but you will not stay there for a long time. Actually, the expected amount of time staying at the region is 0. So which says that you will not observe, you almost always not observe the case that both of the fields are empty. And if alpha is less than or equal to 0, then yeah, you never observe that the queues are empty. And to convince you, I'm not going to prove it because it's very hard. But to convince you why the critical point is 2, you can consider a special case, which is the angle of this boundary is right angle, and the direction of reflection is pointing towards the region. So before calculating alpha, intuitively you will expect something like this. Okay, this guy is doing some diffusion up here, and when it hits y-axis, it will instantaneously go back to the region. And when it hits the x-axis, it will go back to the region. And because of the force here, it will keep stuck at this region. And if you calculate the alpha here is pi over 2, here is pi over 2, and then pi over 2. So it's exactly 2. So that kind of explains why the critical point is 2. So I think that's an interesting result.
So for the original queuing, you don't even care about, you don't even need this result to prove it.
You don't need that, yes, you don't need this result.
When you hit the origin, it's just like the sum of W1 and W2 is equal to 0. And the sum behaves as the original queuing, single queuing storage, where the inflow is AN and the outflow is RN. You don't care about the transportation in between the storages. So
yeah, so because you said the sum is cannot be 0, right? For some positive time, yes. Yes. For the original result, you don't need that. But if you have more complicated queues, then you have that. Let's say if I have something like this. So you have 2 queues, but there are some communication between this one. So there may be some balancing between these 2 queues, even though the inflows and outflows of them they are infinite. Then your domain, your omega may not be even the first quadrant. It may be the value or something else, depending on what's the connection between.
Your example confuses me, because what if your domain's like, an obtuse angle? Then your formula would say it shouldn't go to the center, but then the argument seems to say it would just zoom in.
It should go to the center. This one is
No, but
stuck at the region.
okay, what I'm saying is if you have the obtuse angle, then you do the same thing. right? Shouldn't your alpha be less than 2?
I have a cube,
And obtuse angle.
Choose.
sorry,
Obtuse.
obtuse,
Yeah.
obtuse triangle, so, yeah, obtuse triangle, so this one I can see is value, right? So alpha is smaller.
Right. So I'm saying, but this little argument here just seems to say zoom in.
Wait,
The same example with the
no, because this one is larger, so this one is less than 2, right?
So it
Yes.
shouldn't go the same.
Wait. Let's check. I think I'm missing. Yes, actually, you know what,
It's not like
actually
the
the thing is that we have a restriction on this one. Actually, all of them is restricted. But this one is just the limiting case. Yes. So all the angles, because here it's kind of like pathological because to keep, let's say, to keep the second component always positive, right? So this thing should always be this guy. Positive. And if you want the direction of the reflection to be here, that means that the magnitude of this force is infinity. Right? So this kind of direction of reflection is like physically speaking, it cannot be attained, it can only be in the limiting case. So we can have something like this, will now be parallel to that. That's a good example to show that intuitively why